Okay, welcome back to our second session. We were just discussing the research sector. So the idea is this. There will be a research expenditure, okay, which is called R. So the entrepreneur will spend that valuable resource by purchasing it from the final goods sector. He or she spent that amount for research. When the amount that is spent on research, the amount that is invested in research is equal to R, the total number of machines, new machines that are created is equal to lambda times R. So lambda is a fixed parameter that shows the research productivity. Of course, you can also make this endogenous and time variant. In one particular model, for instance, that I work with, it is endogenous actually. But for now, simplicity, we just assume that there's a fixed productivity in R&D, and the amount that is spent directly creates that flow of new intermediate products, okay, new machines. So now we want to think of this research sector in terms of the problem that they solve, right? So after the research, they have this new the flow of new machines, right? M dot. And for each machine, they obtain a profit. Okay. Now this is profit from research in present value terms. What do I mean by that? Let me show you. So remember that if I produce one of the machines, at any instant I obtain this profit, right? Pi. Okay. Now what I want to look at is the present value of this profit. Okay, so to find the present value, I of course discount it by this term, right? E to the minus RT, as you know already. So if there's a real interest rate in the economy, in the market, so the firms would discount monetary payoffs through this real rate, R. And if you do the math, then you realize that present value is equal to pi divided by R, because pi is constant, pi goes out, and the integral here is very simple to solve. So you have pi over R as the present value of the profit stream from just one machine. Okay, so from one machine only, the entrepreneur will obtain pi over R in present value terms. Okay. But the case is that this research firm or the entrepreneur has M dot new machines, right? So the total payoff is M dot times pi over R. But there is the cost, right? Total cost is R, because the that's the monetary unit that is spent on that instant T. So the net payoff of the entrepreneur is that equation. Okay, M dot times pi over R minus the total cost of research. So obviously, the research sector firms want to maximize this. Okay, so we put M dot. We replace M dot with lambda R, right? But the problem becomes, the objective function becomes linear, right? A linear function of R. So here, we introduce perfect competition and free entry assumptions to make sense of this, right? Because this is like any other perfectly competitive sector with a linear production function, okay? So if there is a profit opportunity, new entrepreneurs enter the market, okay? And they bring down this excess profit opportunity to zero again, okay? So in equilibrium then, with any positive amount of R, no firm should make a positive profit, okay? This requires the interest rate to be equal to lambda times pi. Now, this equation is famous in endogenous growth theory. It is, so there are different versions of it. You're gonna see different versions of this equation, depending on the model's fundamentals. But it is called the research arbitrage equation, right? I mean, research arbitrage in the sense that there will be free entry in the research sector. So if there is a profit opportunity, so if it is profitable to open a startup, people will do that, right? But then if there is enough startups in the economy, then excess profit opportunities will be zero. So in equilibrium then, with perfect competition and free entry, the research sector will always be in equilibrium with R being equal to lambda times pi. And that makes a lot of sense, right? Because that equates cost of funding with the return on funding, right? So the R could be imagined as the marginal cost of research, because now we are spending a valuable resource to it, and lambda times pi would be imagined as the marginal return, right? Because lambda is the productivity of 1 unit of R&D spending, and pi is the profit. So remember the earlier equation, right? Remember the earlier equation. Earlier equations here basically about the supply side of the credit market. Okay, so I have the funds, I'm the household, I have this stock of wealth, and I supply this into a capital market. And then there are firms, they look for funds. They have a demand for funds. So the research arbitrage equation represents their demand for funds. So the equilibrium is, of course, here. Okay, so R and G are two unknowns. Okay, R and G are two unknowns. R is determined by the research arbitrage equation, and it is equal to lambda times pi. Okay, given the interest rate, the growth rate is solved by the earlier equation. As you see, it's a very simple model, just two equations and two unknowns. But eventually, we find the growth rate to be equal to what? The growth rate must be equal to this whole bunch of things. So how many parameters? We have lambda, alpha, L, rho, and epsilon. So you have 5 parameters, in fact, 4 parameters and 1 exogenous variable that explain growth in the economy. So if your research sector is more productive, right? If your research sector is more productive, if the final goods sector is large, if your economy is large in terms of workforce, if you are less impatient, okay, and if epsilon is smaller, then you have a larger growth rate. Okay, so why would government invest in technological capacities of the startup firms? That's the reason, lambda. So if the startup firms become more productive, then growth rate in the long run is larger, ceteris paribus, of course, the other things being constant. Why would a large population is a good thing according to this model? Well, because that increases the profit opportunities of the intermediate goods sector and eventually spills over into the research sector, because profit opportunity is a driver of return from R&D. Okay. So that model is this. Very simple version, of course, we are studying. So if you look at the paper, Romer 1990, Journal of Political Economy, the model there is much more complex, much more realistic than this textbook version. But no model is, no model in economics is realistic enough. The problem with this model, the main problem with this model is this L term, the one you see here, but we're going to discuss this, I think, next week when we talk about the scale effects. For now, I'm leaving that discussion. One thing you may imagine is this. If you look at this payoff of the research sector, you can actually put subsidies here, right? So let me show you a version with research subsidies. So we have maximizing what? Lambda R pi over R, right? And now you may imagine that the government imposes the subsidy for research, right? So S is between 0 and 1, a subsidy rate. So instead of paying RT, the firm is paying 1 minus SRT, right? So this is the startup firm or the entrepreneur. Okay. Now, if you solve this once again, there must be zero profit. So lambda pi R must be equal to 1 minus S, right? So R must be equal to lambda pi 1 minus S. Okay. Then if you put this back into the growth rate, so let's say this is R star, the equilibrium level. So G star is what? It is lambda pi 1 minus S minus rho epsilon. Now, as you see, the long run growth rate depends on the subsidy and they're positively related. Okay. So if the government somehow finances a part of the research spending by the startup firms or the entrepreneurs, then that's good for the long run growth rate of the economy. So that was an important finding because that creates a room for opportunity, room for opportunity for the window of opportunity for the policy making in terms of long run growth, right? After so many generations of economists, they believe that, they wrongly kind of believe that the policy doesn't matter for long run growth. Long run growth depends on technology and stuff, and technology does not really responds to policy. But that was obviously a crude simplification originating from the naive neoclassical models of growth. With endogenous growth models, as we see both here and also in the models of Marshallian externalities, policy matters. You may also imagine other types of policies. For instance, you may imagine that the government can spend some money for making let's say, lambda t to be endogenous. So suppose that lambda t depends on some sort of government spending. Okay. So x, oh, okay, not x. Let's use z. So suppose that z is government spending on research infrastructure. Okay, and S is the subsidy, right? So now you may imagine how to choose if the tax revenue of the government is fixed. Now, how does the government choose Z and S? Okay, to finance the subsidy and also to increase the infrastructure capacities. Okay, and you may also imagine maybe the government itself would be running a deficit. Okay, so you would imagine that there is a debt stock. Okay, and the government may be financing technological investments and research subsidies through accumulating debt. Okay, so if you extend this logic a little bit, you might have a nice paper, right? So because there are many interesting questions here. Okay, let me pause here again. As I said, we discuss this scale effect problem next week. Let me now pause for a moment if you have questions. Otherwise, I'm going to show you another Schumpeterian model. Okay, so the next model we're going to look at is a simple version of Aghion and Howitt's model. So that model was published at 1992 in Econometrica. So the model here is a little bit different because it looks at another dimension of technological progress. Okay, so let me first explain what do I mean by dimensions of technological progress. So typically, in modern growth theories, we have two dimensions of technological progress. Okay, so one is the horizontal dimension, and the other is vertical dimension. Now, on the horizontal dimension, you have, let's say, machines. Okay, so these could be different intermediate products, and in some versions they could be different types of consumption goods as well. Okay, now this horizontal dimension of innovation is called product innovation. Okay, or in some papers it is called entry in the sense that new machines are introduced into the economy, and typically each of these machines or intermediate products would have some attributes we like. So we denote these attributes by AIT on the vertical dimension, right? So these could be quality of the consumer good or productivity associated with a particular machine. Okay, so in the vertical dimension, we call this process innovation. and in some texts, it is called in-house R&D. Okay. Now, at any particular time, at any particular moment, these machines or consumer products have a productivity distribution. Okay. So this is a distribution of productivities for intermediate products in that set. Okay. Now, technological progress means two things. First, there is product innovation. So you have new firms. Let me write this in discrete time. Okay. And then, of course, you have to make a particular assumption about the productivity of these ones, right? So they could be the average, or they could be random. Okay, but you have to assume something about their initial productivity once they innovated. Okay. Now the other type of innovation is on this dimension. Okay, existing products are subject to R&D, right? So the firms already producing such products, they try to increase the quality of them, they try to increase the productivity of them through R&D spending. Okay. So in time, technology progresses in this direction. Okay, there are new goods in the economy that is used for consumption or production purposes. These are intermediate goods, and these intermediate goods become more, more productive. Their quality is getting larger because of research, right? So the first iPhone was a great thing. So it was a product innovation, right? Invention of iPhone, but then there are better and better versions of iPhone in time. Okay. Now the model we just studied, Romer 1990, was about the horizontal dimension. Now Aghion and Howitt's model, Aghion and Howitt, 1992, it is about the vertical dimension. Now we're going to look at it. Okay. So where's my, okay, the Schumpeterian model. And let me now share it. Okay. So this is the this is from Aghion and Howitt's textbook itself. I suppose it is chapter 4. So you may look at the textbook discussion if I leave something out. And here we are starting with a one sector model. Now, the important thing is this. So there's an important difference between the Romer model and the Aghion and Howitt model. So in the Romer model, as you realize, it is a model of creative accumulation, right? So entrepreneurs are creative. They invent these new machines, and it is a cumulative process. M is always getting larger and larger. So once the economy is getting more creative, then they never leave some M out, right? Some of the machines are. They always use all the machines. So it's the creative accumulation model. Now in this version, there is one machine because it's the one sector model. There's only one machine that is used, but what creates growth is the different versions of this machine. Okay, So for different versions of this machine, there's creative destruction. So the new version basically destructs the profits of the older version. Okay, so there's an incumbent monopolist. The incumbent monopolist produces the good with some technology, with some productivity level, but there is a competitor, innovator. If that competitive innovator becomes successful, the new version is being used. Okay, so in that sense, the creation of a new technology destructs the profits of the holders of the earlier technology. Okay, so there's this key difference. And the model, if I remember correctly, let me make sure. Yes, the model is in discrete time. Okay, for simplicity. And there are a number of people in the economy. Okay, so L is the labor force again, and here we are assuming that their lives just one period lives, right? So I open my eyes, I'm at this world. I have this one period of life, and what I care is my consumption. Okay, and consumption. So this is even more simplified. The consumption is a linear version, a linear function of, so utility is a linear function of time. The utility function is a linear function of consumption. Okay, and this of course creates what? This creates risk neutrality. Okay, so there is no risk aversion. Typically, utility functions are assumed to be strictly concave, right? With strictly concave utility functions, decision makers become risk averse. Okay, we don't like to take risks normally, because normally we assume that we have such concave utility functions. But if your utility function is linear, then of course since expectation operator is linear, right? You become a risk neutral decision maker. So here risk neutrality is a simplifying assumption, but also a little bit more realistic, because in such models, if you want to be a technology creator, you have to assume some risks. Okay, so risk neutrality allows us to see what would happen to optimal research if people are risk neutral, right? Because if they're risk averse, then there is this additional determinant of research spending, right? Because research is a stochastic event in that particular model. Okay, and one final assumption is that everybody is supplying labor inelastically, right? So everybody works in the economy. There's no leisure choice. Now the final goods sector uses this production function. Now, as you see, there is only one machine, X. Okay. And the productivity of machine X associated with, so to the productivity level, AT is associated with that particular version of the machine. Okay. So machine creates a labor productivity effect, as you see here. Okay. Now this sector could be competitive once again. So the final goods sector is competitive. So there are many firms that use this technology. So once again, we find the inverse demand for the machine and inverse demand for the labor, right? So that part is the same, except the fact that we don't have the integral term here, right? Because there is only one machine. Then we again find the inverse demand and write the profit of this machine producer. So once again, I want to make sure there is only one machine, and at each T, there is only one producer of this machine. That's the monopolist. All right. So the historical example is James Watt. All right. So he invented the steam engine that can be useful for the production purposes, and he obtained a patent for it. Thanks to that patent, he was the sole producer of steam engines in England for 19 years. All right. So that's type of a model that we are looking at, but only simplifying it with one machine only. Okay. But the problem is the same. And if you solve it, the only difference would be that productivity term 80. So what does it tell you? It tells you that the optimal amount of machines you create depends on how productive your machine is, and again, how large your customer is. Okay, your customer is the final goods sector. So the total labor force employed in the final goods sector will be important for your, for your scale. And also, if your machine is more productive, is getting more productive, you produce more of it. Why? Well, that's again the complementarity of the production process. So if it is getting more productive, firms in the final goods sector are more willing to pay higher prices. Now, again, there is this third sector, innovation or research. Now, here, innovation is going to be stochastic. Okay? And it will take place at the beginning of T, right? So the discrete time model at period T before production takes place. First, we're gonna look at innovation. Let me pause here because I have less than 2 minutes. So if you have a very quick question, I can answer it again. Or we're gonna take a final break and meet for the third session. Okay, so let's meet at, so it is now 10:40. Let's meet at 10:55. Is that okay for everyone?
Okay.
All right. Let's meet at 10:55 and continue with the Schumpeterian model. Bye-bye.
Okay, bye.